So in our last video, we talked about general plane motion and specifically how we can look at acceleration for general plane motion. And we were doing that using relative analysis, right? And so when we talked about doing relative analysis of velocities, we had this special case of rolling without slipping and this special relationship that we had for disks or other objects that are rolling without slipping. And so we're going to have those same things in acceleration, and they're going to work in just the same way. So we're going to do just a couple of quick little examples so you can see what that looks like. So this rolling without slipping, we had, when we have some disk that's like moving this way, and there's the center of the disk, and it's rolling without slipping. We said that for velocity, the center of this disk, so we'll call that G for the center, Vg was going to be the angular velocity times the radius of this disk. Right, so this disk has some radius r, and then it's also undergoing some kind of angular, probably the other way, this angular velocity. And so if we were to take the derivative of this with respect to time, right, dvg dt dt, what we would end up with is our acceleration of g. The acceleration of the center of that disk is going to be the angular acceleration times the radius. Right, and your angular acceleration doesn't necessarily have to be in the same direction, could be in a different direction. But this kind of helps give us a grounding point for these rolling without slipping problems. So let's do like a mini example to kind of take a look at this. So let's say that you have some disk here or some gear running along a track, something like that. And it has an angular, let's say an angular acceleration of 6 radians per second squared, and in the same direction an angular velocity of 12 radians per second squared, and this thing has a radius of 0.3 meters. And so let's say we wanted to find our acceleration of this point A at the top here. So what is the acceleration of A? So what we can do is we can find what this overall acceleration of the disk is first, and then we can use those relative motion equations that we had been working with in the last video to find what it is specifically at point A. And so right here in the center, if I call that point O, I can find that acceleration of O by just doing alpha times r. It's 6 times 0.3 gives me 1.8 meters per second squared. So now I know the acceleration of the disk in general as it's moving. And I know that this is going to be moving like horizontally, right? This is another, since it's constrained to be on the ground and it is the center of this disk, our AO is moving horizontally like this. And then I want to find my AA. What is my acceleration of a specific point A? And so I can use that relative motion setup that we had been using in our last video, where we take our acceleration of A is going to be acceleration of O plus alpha cross product with the position vector A with respect to O minus omega squared times r of A with respect to O. If I start seeing what I've got here and plugging things in, I can find that vector from O to A. That's A with respect to O, and that's going to be RA with respect to O is going to be 0.3 j hats. It's straight up in the y direction there. And I'll start plugging stuff in so that I get 1.8 meters per second squared, or I really don't love putting units in here because it confuses me personally with my I hats and J hats, and I don't usually put these in here. It just gets to be too much of a letter soup. It's good practice. It is best practice is to put your units in there. We're already writing so many things out. For me personally, I'm okay with just putting units at the end, just keeping all of your units straight and knowing what units you're putting in there. But gosh, it can get a little messy with all the units in there. So 1.8, we said this is moving in the positive x direction, so 1.8 I hat is what our acceleration is. Plus that alpha they gave us is 6. And notice it's going clockwise, so this is the negative k direction. Negative 6 k hat. Cross product with our position vector of 0.3 j hat minus omega is 12. So minus 12 squared times that position vector again is 0.3 j hat. So then we can go ahead and solve this out for our acceleration of A, 1.8 I hat, and then k cross j is going to be an I hat, a negative I hat, so plus 1.8 I hat minus 43.2 j hat, which gives us a final answer for the acceleration of 3.2 I hat minus 43.2 j hat meters per second squared. And maybe they want maybe they want the horizontal and vertical components, maybe they want it in this form, maybe they want the magnitude where you take the square root of the squares to find what that overall acceleration is. But this would be a perfectly fine answer for just, if they ask what is the acceleration of A, it's 3.2 I hat minus 43.2 j hat. So that was a fairly simple example. Really, these rolling without slipping problems aren't terribly complicated. It's just a matter of keeping those directions straight, making sure that you're using the appropriate formula at the appropriate time, right? So using that AO equals alpha times r only for the center of that disk, and then using your relative motion otherwise. But we'll do one more quick example so you can kind of get a feel for it a little bit more. Alright, so in this example, we can see there's a spool shown that unravels from the cord such that at the instant shown it has an angular velocity of 3 radians per second and an angular acceleration of 4 radians per second squared. Determine the magnitude of acceleration at point B. So, although it may not feel intuitive necessarily when you look at this problem right away, this really is acting just like a rolling without slipping problem. The only difference is that it's moving downward, right? Instead of moving horizontally, as we would normally expect it to, like rolling across a table or something, the spool is falling straight down, and it's unraveling there at A. So it really is acting like a rolling without slipping problem, just unfurling that spool. Where what we have instead that's just a little bit different is that acceleration A is downwards. And so what we're going to see is we've got that acceleration downwards there, and then we have our position vector of B with respect to G, and then we know that that acceleration at B is probably acting like somewhere down and to the right, most likely. Just if we had to guess, that's probably what our acceleration of B would look like, since we have these angular velocity of 3 radians per second, angular acceleration of 4 radians per second, they're going clockwise. And so we're going to say this spool is unraveling, and we're going to say it's not necessarily subjected to gravity. Like, we're not really accounting for forces or anything in here. We're just going to find the acceleration of the spool kind of as it unravels, rather than thinking about it in like gravity and forces kind of way. Right? Just kind of as it rotates outward, maybe someone is pulling this spool out downwards instead. So the way that I am going to start this is that I am going to find this AG, this acceleration of it downwards, because I know that AG is just alpha times r, and this alpha they gave us is 4 radians per second, and the r, if we pay attention, the r is actually where the cable is connected. That's where this thing is really kind of rotating around. So that acceleration is dependent on that inner radius of 0.5, where the spool is. Since that spool doesn't go all the way to the outer edge, it's not rotating all the way out to the outer edge. It's only that 0.5 feet there, which gives us an acceleration downwards of 2 feet per second squared for AG. So now we're going to go ahead and do our relative motion setup with AB, since we're trying to find it about point B. AB is going to be AG plus alpha cross R of B with respect to G minus omega squared times R B with respect to G. So I can go ahead and plug my things in. I'm looking for AB. AG I know is 2, and that is in the negative y direction, so negative 2 j hat. Plus my alpha, I notice we're going clockwise, so by my right hand rule, my thumb goes into the page. That is negative alpha k hat. Cross product with my position vector is now the larger radius, right? It's that 0.75 all the way from G to B. 0.75 j hat. Minus my omega value, 3 squared, times that position vector again, 0.75 j hat. So simplifying that out, we're going to get negative 2 j hat. K cross j is negative I, so I'm going to get a plus 0.75 alpha I hat minus 3 squared times 0.75 is 6.75 j hat. And then they did ask me for magnitude. And oh, I don't know why I wrote alpha every time in here. I know what alpha is. It's 4. I don't know why I didn't plug that in this whole time. Okay, let me simplify this and actually plug that in. Negative 2, I can combine those j's together too. Negative 8.75 j hat plus, if I plug in a 4 in here, I'm going to get 3 I hat. So now I can actually find the magnitude of this thing. Square root of 3 squared plus 8.75 squared means the magnitude of my acceleration of B is 9.25 feet per second squared. So overall, not too bad, just a matter of keeping a few of those special rules in mind when we're doing these rolling without slipping problems.